Good morning, everyone. My name is Kevin Jamieson. I'm a professor here at the University of Washington in computer science. And I work on a topic called bandits, multi-arm bandits. Rob's lectures and Seb's lectures over the past few days have been dealing a lot with having how to operate and make inferences from a fixed collected data set. So historically, we have some amount of data that's been collected, and we want to do some sort of optimization on it, or we want to learn some sort of function of it to predict on future data. What I'm going to talk about over the next few days is actually how do we collect that data in order to achieve specific tasks. Okay? So while the last 10 years has really been dominated by exploiting machine learning to learn things about past data, to use them on future data, what the next 10 years I think is really going to be about is all about interactivity. And by interactivity, I mean it's more going to be a conversation. Instead of learning on past data and exploiting or using this policy on future data or future interactions, it's going to be more of a discussion. A discussion much more like what could be possible with something like an Alexa or some sort of robot like this, where you're asking for a question, and then there's a response, and then there's a give and take back and forth, a discussion about honing in on what you're looking for. And what that's going to look like, to visualize this sort of idea, there's lots of things that you've experienced in your life that has bandits all around you. Unlike supervised learning and machine learning, where it's very, very popular in the news and it's very clear how it's impacting your life, sometimes it's not obvious how bandits are interacting and affecting your life. So as an example of how ubiquitous bandits are, I love the New York Times because it's just a plethora of bandit algorithms running in the background. First of all, there is no such thing as a typical web experience these days. There's so many A/B tests being run on this browser right now. Even though I'm in incognito mode, I still have features like I'm in Seattle right now. And so I might be bucketed into some demographic. They also have other information about my IP address that they can exploit from historical interactions. And by doing this, they're trying to figure out what works best for me, what works best for this demographic, what headline should I be showing. All the big headlines on this page, if we all go to New York Times, we're going to see different headlines because they're actually A/B testing them to see which ones are actually getting you to click on these articles as much as possible. We also see a big ad on top. We're also trying to maximize the amount of click-through rate on that because the New York Times is paid by the click or by the amount of subscriptions that people show up to. And so we're trying to make these ads, as appealing as possible in order to maximize revenue. But these are more sort of explore-exploit sort of tasks, where I don't know your preferences. I don't know if I have 10 ads I could show you. I don't know which ones are going to work. And so I'm going to have to balance this exploration of learning what works and then transition over to exploiting what works after I figure this out. But there's also other tasks that are much more exploratory. For instance, something like, I like this tool. This is something where if you are trying to find a coffee table, which is a very, very difficult problem, this tool is going to actually help you find that. And the way it's going to do that is you have some coffee table in your head, and you're going to look at these different coffee tables that are here, and you're going to say, like, yeah, I'm looking for something that's more roundish, say. And if I keep clicking on these things that are round, these coffee tables are going to eventually hone in on what I'm looking for. And it's a tool that is just pure exploration, right? I'm not trying to get as many good coffee tables on here as possible. It's trying to, the ones that are showing up when I click like or dislike, the ones that are showing up are the most informative ones that I can ask. So if I ask plus or minus on these ones that show up, they're the most informative query that can be made in order to hone in on my preferences over these coffee tables as quickly as possible. Likewise, you could be a drug maker bringing a drug to market, and you have to figure out all the different drugs that are the best possible to bring to market, but you're only going to bring one. Right? So this is, again, a pure exploration problem. We have this offline process where you're doing lots of exploration. You're trying lots of different drugs out. It's a very noisy process. And once you find one, you're going to go bring that one. You're going to take that one to market. So drug companies do this quite a lot. Also material science. Material scientists are often looking for a specific peptide that binds to a specific surface in a maximally way. Like your toothpastes are just peptides, and that was found through an optimization process, much like a Bandit process. And these are, again, pure exploration problems. The final example I have is of Google Maps. So you might have, this doesn't happen so much to me anymore, but a couple years ago, I used to live in San Francisco, and whenever I would take an Uber across town, sometimes I'd be routed on some really, really strange routes, and basically through alleyways and things like this. And whenever I was routed on those sort of things, I knew that I was being routed that way because I was part of a Bandit algorithm. They have to figure out what are the best routes to this city. They have a model, a very useful model. It's pretty good. But they are constantly trying new ways to get through the city. And the city is constantly changing. It's somewhat of an adversarial environment because everyone's sort of competing for the same space. And different algorithms can help you get routed through these paths from A to B as efficiently as possible. And of course, content recommendation. So Spotify, Netflix, all these are different interaction techniques or interactive modalities that are trying to explore your preferences, what you like, and also exploit them, give you content that you want. And so these are all sort of intertwined with machine learning and supervised learning, where we're getting data from you, and then we're trying to learn some model, in order to exploit your preferences. But that core question of what data do I collect from you? What is the next question that I ask of you in order to get as much information about your preferences while also possibly respecting the fact that I can't ask you bad questions because you'll leave the site. And so I have to balance sort of this exploration versus exploitation. And so over the next few days, what we're going to do is basically look at algorithms that balance this trade-off and how to optimally collect data in order to make these kind of inferences. And in essence, Bandits is closing the loop on inference and data collection. Instead of just making inferences from a static data set, we're closing this loop and making inferences and data collection in a very closed cycle. OK. So let's just dive in. So the name, multi-arm bandits, is a let me just turn off Wi-Fi here, just in case. The name Bandits has a bad, stupid history, but it's basically in a casino. When you'd walk into a casino, you see a slot machine. It would, you pull down the thing, and then the three things come up, and you either win money or you don't, right? And now this is a stochastic process where when you pull down that lever and you get some reward, is a stochastic process. And this is called a one-armed bandit because they take your money. And you're trying to win against this bandit. A multi-armed bandit is when you have, say, K slot machines. And now maybe some of these slot machines pay out more than others. And so I'm going to try and figure out which slot machine is paying out the most so that I can go and exploit that one and only use that one forever. OK? And so the way that we're going to process this, or the way that we're going to model this whole process, is through a stochastic model. And we'll start there and then get more advanced as we move along. So what we're going to assume is that a very simple sort of interaction model to begin with. And we'll build up over the time to a more complicated one with features and things like this. So simply, input. That doesn't look very good. Say n arms. OK? And this terminology, again, is that I have sort of n slot machines, and I'm going to call them arms. And when taking a sample from that slot machine is pulling it. OK? So I have n arms. And now the game is defined as for t equals 1, 2, ... Algorithm pulls arm it, some index, in 1 to n. This is what I'm using to index this. This notation of bracket n is just 1 to n. And then nature reveals RT from some distribution, so stochastic process. I'm going to call PIT, some IID distribution. So anytime I pull the ith arm, I get some observation from the ith distribution, where expected value of RT, I'm going to say, is equal to RT given IT is equal to theta star IT. Okay? And so for each one of these arms, I have a different distribution with an unknown mean. So I have these theta star I for the ith mean, and I don't know what it is. And what we'd like to do is be able to simultaneously explore and exploit this situation. And so to motivate this, Thompson, in 1933, wrote this beautiful paper on multivariate bandits, introducing the modern interpretation of it, where he imagined the situation of a doctor, where symptoms, patients would come to him one at a time with the same symptoms, right? And now he's got n different treatments he can give. And so the patients come to him one at a time. He gives them a treatment. They go off. They get better or they don't. And now what he's trying to do is figure out what is the best treatment and only use that one for the patients that come. And so here the patients are arriving one at a time. IT equals 1, 2, 3, 4, et cetera. The doctor chooses some treatment IT at time t, and then he reveals some reward. The reward is, say, the patient living or dying. And now you're trying to maximize the amount of reward or maximize the number of people surviving through this process. Okay. And now what goals we might have are either regret minimization, or maximizing the amount of reward, or pure exploration. So in the regret minimization, we're going to define the regret as essentially competing with the best offline policy. So if we know that there are n arms, and one of them has the highest mean, a natural thing to compete against is just playing the best arm every single time. Okay? And so I'm going to define the regret after t time steps. Okay? So what this is saying is the most reward I could possibly get in expectation is going to be just playing the best arm every single time, the one with the highest mean. But what I'm actually playing is a different arm every single time. And what I want to do is maximize the expected reward of what I play. Now, this is not the only way that I could define regret. Right? And I'm saying regret because this is how much worse I'm doing than playing the optimal policy. But it's not the only way I could define it. I could define it as actually the expectation of the max inside the sum. So there's some stochastic sort of process that I would, from any given arm, if I keep playing that one arm, it's going to have some stochastic process. And then I could say, well, what is the best one of that stochastic process? And that would deviate a little bit from its mean and wouldn't necessarily be the one of the highest mean. And we'll return to this when we see adversarial bandits later in the week. But for the purpose of these lectures, we're going to look at the stochastic setting. And in any case, any stochastic process of the expected or the average returns are going to concentrate towards its true mean very, very quickly. And so this is how we're going to define this regret, which is sometimes called the pseudo-regret. And the objective here is what we really want to have is the goal of all this is to have RT choose these rewards or choose these actions and get rewards such that the regret is little o of t. Meaning that, and this is called sublinear regret. As time gets very, very large, I'm relative to the best policy, I am converging to it. Okay, I'm getting very, very small rewards. So, if I divide by big T on both sides here, I see that I am competing with the best policy asymptotically. And so the first sort of result that you'd like to have is turning this into something a little bit more manageable. And the way that we're going to do that is a very simple little lemma. Just do some simple manipulations. If we look at this quantity here, I'm going to rewrite it as just sort of breaking it up into the events where at time t, I'm playing arm I. So this is equality, because only almost one of these is going to be on at any given time. But now what I can do is I can bring the expectation in, and RT, given, because now I'm conditioned on this event that IT is equal to I, RT is now a independent random variable with mean theta star I. Right? And so then what I can do is I can just write this because the expected value of that RT given I is just theta star I. Yes?
So in the original regret, what's the expectation over? Because I don't see why you can't take that in there.
The original regret is, the expectation is defined with respect to the randomness of the algorithm, because the algorithm can be doing a random policy, and it's with the expectation with respect to the random rewards that I received. And so I can bring this expectation inside here, and now that I know that IT is equal to I, the expected value of RT is an independent reward from arm I, and so that is just equal to theta star I. And I can bring this theta star I outside this expectation as well.
I guess what I'm confused is, after goal, you have an expectation of RT. Is RT a random variable, or is
I'm sorry. No, I'm defining RT as being the expectation. My apologies. So once I do that, I can bring this theta star outside, and I can define this as just being where I'm defining Ti as the random quantity of the number of times that I've played arm I. Right, it's a random variable. And now I know that if I play theta star I, I is equal to 1, then I'm just equal to the argmax. So I'm going to assume, furthermore, that if I assume that the means are sorted, so that the means are sorted from the biggest one is theta is arm 1, and then 2, 3, 4, etc. I can always do this without loss generality, as long as the algorithm is symmetric. So Then when I play arm 1, I get 0 regret. I don't pay anything for that. And so I'm only paying for regret on those arms where when I'm not playing the best arm. And so then what I can do is I can summarize this as just playing the sum over 2 to n of theta star 1 minus theta star I times the expected value of ti. Okay? And often we'll call this quantity, the difference between the best arm, arm 1, and the ith arm, as the gap between the best and the ith arm. And we're going to notate that as big delta. And so immediately what we see is that the regret, if we wish to minimize the regret, we want to minimize the expected number of times that we play a suboptimal arm. A very reasonable objective, an intuitive objective. And so this immediately brings up, well, if I can identify what the best arm is, if I can identify arm 1 as fast as possible, then and minimize the number of times playing these suboptimal arms, maybe that's a reasonable policy. Right? So a very related objective is best arm identification. Okay? Fix some delta in 0, 1, some confidence. And the objective is to identify argmax theta star I with probability greater than or equal to 1 minus delta using as few total poles as possible. Right? Yes?
One delta somehow be related to t in some sense, right? Because if you have a lot of time, you can explore which is the best arm for a long while before you start gaining.
That's a great comment. So in the regret minimization game, for the purposes of these lectures, I'm always going to fix some time horizon in the a priori. So I'm going to be playing this game for t time steps, big T time steps, and then I want to, within those t time steps, I want to minimize the regret over that time. In the best arm identification game, what I'm going to say is I'm going to fix some little delta, and I'm not going to put any restrictions on the time horizon. I'm going to say you can take as long as you need to go and identify this arm, the best arm, but you must have this condition that if you return me an arm, it better be the best arm with probability at least 1 minus delta. These two are different games. And I will relate them over the next hour. Yes?
And did you make any assumption on whether like the n arms have the same sort of underlying distribution, they're all normally distributed or something like that?
Yes. So under both this game and this game, this is the same protocol. Okay? So they share this protocol in that at each time the algorithm decides what arm to pull, and then nature reveals some distribution, a reward from that distribution, and their distributions are the same. And furthermore, I'm going to restrict the kinds of rewards that I'm allowed to see. So I'm going to assume that each PI is one sub-Gaussian. You've seen sub-Gaussian rewards in this series, haven't you? Okay, let's go through it then. So, by definition, a random variable is sub-Gaussian distributed, is one sub-Gaussian distributed. Let's say R sub-Gaussian distributed. If is equal to that. Okay? This seems like a strange definition and somewhat unmotivated, but it's a moment-generating function, so it shouldn't be that strange. But what we can do with this is that it turns out a lot of distributions have this property. So for instance, if x is bounded in AB, then r squared is equal to b minus a squared over 8, I think. I'll check that in a moment. We'll get back to that. This is Houghton's inequality. I always forget this constant downstairs. But also, if x is, say, Gaussian 0, 1, then r squared is equal to 1. Okay? And so we have these very natural things here. Yes. Thank you. And then so what we can do with this, though, is apply apply Chernoff bound. So Chernoff bound says the following. Suppose xi for IID 1 sub-Gaussian. Okay? Then what we're going to prove is that the probability that I equals 1 to n of xi, and so it's 0 mean, greater than epsilon is less than or equal to e to the minus epsilon squared over 2n. Okay? And the way that we're going to prove that is through a method known as Chernoff bound. So I'm just going to erase this, get to the punchline. So this is an extremely common tactic to getting high probability bounds on different random variables, sums of random variables, independent random variables. And it begins very simply by multiplying both sides. Pick some lambda greater than 0. Pick any lambda greater than 0. And now multiply lambda on both sides, and then exponentiate both sides. Okay, so I haven't done anything. I've just applied the same monotonic operation to both sides. And so and now I note that this random variable is a positive random variable, and I can apply Markov's inequality. Markov's inequality just says for any positive random variable y, probability that y is greater than t is less than or equal to expected value of y divided by t. It's a good exercise to prove this. Maybe we'll do that. I'll add that to the section handout. So if we do this, then what we get is e to the minus lambda epsilon as the expected value of x lambda sum over all the i's. And now what we observe is that this is a product of a bunch of exponentials. If I bring the sum outside the exponential, or something like that. And by assumption, each of the xi's are IID. They're independent. And what that buys us, what that allows us to do, is actually bring this expectation inside. Because if x and y are independent, then the expected value of xy is equal to the expected value of x times the expected value of y. So I can bring this inside. product over all I. But now, again, using the fact that these are IID, the expected value of lambda xi is also just equal to the expected value of lambda x1, just the first one, because they're all identically distributed. And then, furthermore, I'm going to plug in our definition of sub-Gaussian distribution to say that this thing is all less than or equal to e to the minus lambda epsilon times e to the lambda squared over 2 to the nth power. Because what I'm doing is I'm producting over all these. I'm just turning this product into this expectation to the nth power. And so each one of these quantities is less than e to the lambda squared over 2 by assumption of the sub-Gaussian property. And I just get this expression. And now, what I can do, because lambda was arbitrary, I can optimize over. I can choose the lambda that maximizes the expression inside the exponent. And I get that this is e to the minus n epsilon squared over 2n, which was the punchline. OK?
So the r squared is about bounded x, is that right?
R squared, so to have this property, it doesn't necessarily need to be bounded. So for instance, the Gaussian distribution is not bounded. But it has, so if x is equal to the variance sigma squared, then r squared is equal to sigma squared. So that's not a bounded distribution. It only has to do with the moments of this distribution. So it's basically how quickly do the tails fall off of these low probability events. How fast do these things go down as I get further and further away from its mean?
The equation in the lower right there is the r squared.
Here I assume that they were one sub-Gaussian. Yeah. And so r is just equal to 1. And now I can always just scale this by a constant factor, and it will be scaled appropriately. Any questions on that? All right.
So you got to the very last part by optimizing the exponent?
Yes. Calculus. All right. OK. Running out of space, but I kind of need all of this.
Can you read out the last exponent?
Yeah. Oh, sorry, that's terrible. Maybe we'll just put it over here. Just multiplying by 1 over n on both sides. Like that. Can everyone see that? Yes.
Best arm identification problem, do we make an assumption on the minimum gap?
Yes. Yes. I'm going to assume, good question. There's going to be a lot of caveats in these lectures. I'm going to make a number of simplifications so that the proofs are much simpler. But then all of these issues can be dealt with. But one of the assumptions that I'm going to make is that all my distributions are sub-Gaussian. This can be relaxed. And there are many extensions to relax these conditions. Another thing I'm going to assume is that for the best arm identification problem, I'm going to assume that the best arm is unique. There is some finite gap between the best arm and the second best arm. A reasonable question could be, instead of saying, with probability 1 minus delta, identify the best, you could put this in an epsilon delta pack setting, where you could say, with probability 1 minus delta, return me an arm that is at least epsilon within the best arm. Okay? And much of the things almost all the algorithms I'm going to talk about, you would just simply stop early, and you would get this condition without much difficulty. But this is actually one of the, extending all these things to epsilon good is not the most difficult problem if you don't care about log factors. But to get to optimal things, this is actually somewhat of an open problem in some regimes. And that reminds me of other caveats for these lectures is that I'm going to be pretty liberal with constants and log factors in order to minimize the length of the proofs and the difficulty. But I assure you that all these things can be simplified. OK, let's jump in to our first algorithm then. Yeah. Yes. Is that?
Are we always assuming the reward distributions there?
Yes. We are assuming that our distributions are stationary. That if I pull an arm at time t, or time 10 versus time 100, and I pull that same arm, I'm going to get an IID observation from that arm. Okay? That's critical to Bandits. That anytime I take an action, I'm going to get a same IID response. So the first algorithm we're going to look at is going to be a very simple action elimination algorithm. Can we get the board moved up? And so, because if I were just to ask you, if I have, say, n coins, and they all have different biases, right? Some are probability of heads 0.75, 0.5, 0.25, et cetera, and you don't know what those means are, what's the most, and I asked you, go find the best one. It's a very, very reasonable strategy that anyone would come up with. It's just sort of, OK, armed with this inequality over here, if I pull an arm enough times, I can now build a confidence interval on it. And then I can use these confidence intervals so that if I have any two arms, I can then decide that this arm is surely better than this arm. OK? Because I can rearrange this inequality to say that, following on to this point, with probability 1 minus delta, I'm just if I put this equal to delta and I solve for epsilon, I have that 1 over n is less than or equal to the square root of 2 log 1 over delta over n. Okay? All I've done here is I've set this equal to delta and solved for epsilon. And then I have that this is this. And so that with probability at least 1 minus delta, this sum, this empirical mean, is less than or equal to this thing that's going down like 1 over square root of n. Which is very intuitive if you're familiar with the central limit theorem, is exactly what this says. And so if I have two arms, if I were to pull two arms, so I have n is equal to 2. And I have, again, theta star 1 is greater than theta star 2. If both arms are pulled tau times, and I've just fixed this tau in advance, okay? Then the probability that any one of them deviates from its mean by more than square root of log 1 over delta over tau is equal to delta. So the probability that if I define the event EI as equal to the event that 1 over n, tau, 1 to tau, of x, say I, t, is greater than, let's say, square root of 2 log 4 over delta, then what we can say is that because that sign had nothing to do with it, right? The fact that I was going for an inequality here that was greater than epsilon, I could always go through the same sort of analysis with minus xi's instead of plus xi's, right? And by going through the same process with minus xi's instead of positive xi's, then I can get a two-sided interval. And so the probability that this event complement is less than or equal to delta over 2. Because it's the probability that EI complement occurs is the probability, I want that to be less than or equal. EIs are good events. EIs are always going to be good events in these lectures. EI complements are going to be bad events. And so the probability that any one of these fails for each I, for I is equal to 1 and 2, because I have 2 arms, without the absolute value, I have just this thing over here. But the probability that it fails with either the xi's or the minus xi's is going to be the sum of those probabilities. So instead of having each for the positive xi's is delta over 4. For the minus xi's is delta over 4. And so the probability that either one fails is less than or equal to delta over 2. And moreover, the probability that E1 complement cup E2 complement is less than or equal by union bound is less than or equal to delta. Okay? Now, what we're going to do is now say if I want to minimize my regret, what am I going to do? So the simplest possible thing you could imagine is if we define delta as equal to theta star 1 minus theta star 2, this is the gap between the two means, then if I set tau as equal to the square root, the ceiling of 2 delta minus 2, 8 delta minus 2 log 4 over delta, then using on these good events, because with probability 1 minus delta, both these events occur, then what we have is just that theta hat. This is our empirical estimate after, if I define this as being theta hat 1, theta hat 1 minus theta hat 2 is greater than or equal, well, I'll just say equal, to theta hat 1 minus theta 1 plus or minus theta hat 2 plus theta 2 plus theta 1 star minus theta 2 star. So all I've done is added 0. I just added and subtracted theta 1 and theta 2. But this is equal to delta. And this, each one of these quantities, is less than or equal to delta over 2. Is greater than or equal to minus delta over 2. The reason why is because if I plug this value of tau into this expression, I get exactly out that this is less than or equal. Everything cancels nicely so that I see that this guy, sorry, that must have been confusing. Because the xi's, so actually this is this. Okay, because I have to deviate from its mean. I apologize. Sorry about that. This is a zero mean random variable. The inequalities I was proving over here is for zero mean random variables. And so if I have this sequence, this sum of random variables that are mean theta I star, I need to subtract off theta I star, so that's a zero mean random variable. What this means, though, is that I have that each one of these guys, the confidence interval is saying that these guys are bounded between negative delta over 2 and delta over 2. Yeah?
Knots are the sums, right?
Yes. Okay? And each one of these guys is equal that guy, the zero mean random variable. And so I'm just using this tail-bound inequality for the value of tau that I chose, and I see that this deviation has to be at least minus delta over 2. This deviation has to be at least minus delta over 2. But this deviation is equal to delta. And so what I get is that this guy has to be greater than 0. Right? And let's just, because these are inequalities, I can always make them strict equalities without losing anything, just for presentation. And so what this means is that if I pull each arm tau times for this value of tau, I have that if I just look at the empirical means, the difference of these two, theta hat 1 will be larger than theta hat 2 with probability 1 minus delta. This is a signal that I can then use to go and say, I have detected that theta hat 1 is the best arm. It has a higher mean than theta 2 because I have that these using these tail inequalities. Okay? Is there any question on that? Yeah?
This last equation holds with probability 1 minus delta.
That's right. So on the event E1 and E2, this event holds deterministically, but this event holds with probability at least 1 minus delta. Therefore, with probability 1 minus delta, we have that theta hat 1 is going to be greater than theta hat 2, and it's some signal that 1 is the best arm. Yes?
Is there any lesson how do you improve on this confidence as you increase tau?
Sorry, can you repeat the question?
How do you improve on your confidence as you increase tau?
Okay, so you can see that over here. Since the way we got this bound was by setting this equal to delta. So in this expression, n here is equal to tau. And so as tau increases, the delta is going down exponentially. So it's a very fast drop-off. OK. What are we going to do with this? So this basically solves the best arm identification problem because we have identified the best arm. But the issue with this is that we have we needed to know delta, so that's an issue. But we'll get back to that in a moment. I don't like this pen. But I want to talk about regret. So RT, ooh, that's a good color. Again, going back to our expression, is going to be theta 1 for this example, minus expected value, plugging in our lemma as theta star 1 times the number of times I played T1 plus theta star 2 times the number of times I played T2. If T1 and T2 were the total number of times I played arm 1 and arm 2, so that T is equal to T1 plus T2. And what we immediately see is that then this is going to be just equal to, I bring this guy inside here, and I just get that theta star 1 minus theta star 2 times the expected value of T2. Right? And then that is just equal to the gap times the expected value of T2. But now what I'm going to do is I'm going to add and subtract to 0 again. Because I can rewrite this as delta times the expected value of t2 times the indicator of E1, E2, the good event happening, plus T2, E1 complement plus E2 complement in E2 complement. So if the event fails, these are just indicators. So if the event inside is true, it's 1. If the event inside is true, is false, it's 0. And now by definition, an indicator is always less than or equal. So on event E1 and E2, I'm going to pull T2. Basically, I'm going to pull each arm tau times. So I'm going to pull T1 tau times, T2, arm 2 tau times. And then I'm going to make the determination that arm 1 is better than arm 2. OK? On E1. So on E1 and E2, if this event holds, I'm going to successfully determine that arm 1 is the best arm, and then I'm going to play that for the rest of the time. OK? So on this event holding, T2 is going to be less than or equal to, or is going to be identically equal to tau. OK? So that's just equal to tau. Plus T2 if this event does not hold. I'm going to trivially upper bound T2 by all of t. And so what that gives us is just big T times the expected value of this event, which is just the probability, which this is less than or equal to delta. Right? And so this whole thing is just going to be equal to delta, the ceiling of 8 delta minus 2 log 1 over delta plus delta t. It's a big delta missing. I have a delta minus 2 here, a delta here. Ah, thank you. OK. Now, the punchline. So the point here is that if I set delta, this is the true regret. And so if I set delta, little delta, do it in a different color, equal to 1 over t, then what I get is that this expression just evaluates modulo integer effects. This is a 4. I'm going to add 1 to it. This thing is greater than 1. What I'm going to get is delta minus 1 log 8 over delta, where I've just swallowed the ceiling into the side the log. Plus delta. Because I've set delta, little delta equal to 1 over t before I started the game. Okay, and so now what I've done is I've bounded my entire regret by 8 big delta minus 1, the gap inverse, times the log of t. This is good. Remember what our goal was? Our goal was to minimize the regret over time. So as big T gets very, very large, we have that our regret is sublinear, meaning as T gets very large, I am converging to the best arm. On average, my regret is going down. And having a logarithmic regret is really great. However, for big T small, this could be a very, very bad result, right? Because if the gap is extremely small, if delta is extremely small, then this could be a very, very large quantity. And now the other observation you should make, though, is that deterministically, the regret is always less than or equal to delta t trivially. Right? If I were to just play the second best arm every time, I'd be incurring a regret of delta at each time for t time steps. And so then from this inequality and this inequality, what I can conclude is that RT is less than or equal to delta, trivially, plus the min of 8 delta inverse log of 8t and delta t. This is for any delta. And if I assume, additionally, that these gaps are, say, bounded, this is just to give the problem scale. Meaning that the means are bounded between 0 and 1. Again, this is just for scale. I can then say that this is less than or equal to 1. And then I can take the worst case delta. And if I take this worst case delta, then what I get is 2, I match terms, and I get square root of, I believe, 8, square root of 8t log 8t. Right? Yes. I think. Basically, I'm just taking the delta that maximizes this minimum, and I get something that's going like square root of t. And so the point here, though, that I want to make is that because we have this expression, because we have this expression, we get that it is less than or equal to this. The regret is always bounded by this minimum. And what that allows us to do, if we were to plot what the regret looks like, as a function of delta, so if this is RT, and I plot this function, or so it's not really RT, I'm plotting that on the y-axis, then what this looks like is it goes up linearly with delta up to some point, which is equal to this basically equal to 1 over square root of t. And then it starts to go down. Okay? And so what we see is that if delta is very, very small, then we pay very small regret. It doesn't matter what you do. You will not be able to identify what the best arm is, but if the gap is tiny, tiny between the two arms, then you're not going to pay anything for it. On the other hand, if the gap is very, 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 very large, then you're going to be able to find out what the best arm is very, very quickly. And so because you're going to find out what it is very quickly, you're going to pay very small regret identifying it, and then you're just going to play the best arm for the rest of the time. And what this worst case is basically when the gap, delta, is about equal to 1 over square root of t. And we'll see this over and over, where basically 1 over square root of t, or delta, if we equate these two, basically it's this time when t is on the order of the gap inverse squared. And this is how much time it's about going to take in order to identify which arm is bigger and take the appropriate action. And with that, I am out of time. Is there any questions on this? Yes?
I'm a little confused about how the EI events are defined in this case, because it seemed like we were assuming that they were both pulled an equal number of times. But here we just do t time steps, and then t1 and t2 are random.
Yeah. So I implicitly had an algorithm here, which is pull each arm tau times, and then pick argmax I theta hat I, and play it two tau times. Right? So on even times, say I'll play arm 1. On odd times, I'll play arm 2 for tau times each. And then so once I've played 2 tau total times, I'll compute the empirical means. I'll take the best one, and I'll play that one for the rest of the time. Okay? So t2 and t1 are random variables that are based on this determination of did I pick the best one or not.
It's as similar as playing each arm sometimes and then just
taking the largest sample average?
That's exactly right, yes. It's as simple as that. This is the simplest possible game you could play.
And then just set a lower bound to tau so that you have this condition for delta.
Precisely.
But you don't know that.
Yeah, and that's the problem. In practice, we'll never know what delta is. And so what we're going to talk about over the next few lectures is how do we come up with algorithms where we have more than 2 arms and where we don't know what delta is and we don't know how long we're going to be playing this game for. How do we deal with this? How do we effectively do best arm identification or regret minimization in order to solve these problems?
Your algorithm does extend naturally to that case, though, right? Like, I can pull each of multiple arms as many times as I want, pick the argmax, and go with that.
Absolutely. No, it's an excellent point. So what we've really found here is that for this particular value of tau, we have optimized tau here so that right when we can identify what the best arm is, we're defining tau as that. So we've tuned tau perfectly here. So what would happen if we had tau less than this value? So if tau was significantly smaller than this value, you'll just have to take my word for it. We'll see it later in the lectures. What will happen is that we will make a mistake with some constant probability. And therefore, with some constant probability, we'll get order t regret. On the other hand, if tau is much larger than the value that we specified here, then we put too much time into exploration. And we will incur additional regret because we're playing arm T2 too many times, arm 2.
So what do you mean we don't know delta? Don't we set delta as the quality of this process?
Sorry, this is a notational disaster on my part. I'm defining big delta, yes. Little delta and big delta. I'll try to not say delta. I'll try to say delta for the confidence level delta and gap for big delta.
If we have more than 2 arms, do we get the same result? Should
No.
be t to the 2/3, right?
So what he's alluding to here is that if I have more than n arms, then more than 2 arms, then how does this result extend? And yes, it's true that you can still play the same algorithm, and you can still sort of tune tau in the optimal way, but you will never get sort of an optimal sample complexity. But what you can do is pick tau in such a way, I think tau being equal to something like, I always forget what it is. I think it's t to the 2/3 or t to the 1/3, and then you can always guarantee that the regret is going to be t to the 2/3, which is significantly worse than our square root of t regret. And we'll see examples of this in the future.
And do we care about dependence on n or not?
We certainly care about dependence on n.
We make that worse by making this.
Yes, we're going to care about the dependence on n, but in particular, we're going to care about the dependence on all the gaps. All the gaps between the ith arm and the best arm. Because if the problem is very easy, meaning there's a lot of large gaps between the ith arm and the best arm, this problem, we should be able to use fewer samples and get less regret. OK, see you next time.